Good evening. I'm Spot On Weather meteorologist Matthew Euler, and welcome to my latest video presentation. In tonight's video, I'm going to focus on the QBO. Now, what does that stand for? That stands for Quasi-Biennial Oscillation, and I'm going to look at that specific oscillation or teleconnection and examine that along with what happens typically in U.S. winters. I will show you some temperature anomalies and precipitation anomalies, examining the QBO for the U.S. winter seasons. I will also heavily focus on the temperature anomalies. I'll show additional data with the various phases of the QBO and what type of temperature anomalies we see. Now, on tonight's title slide of the presentation, what I'm showing you are different colors here. So you notice the maroon coloring or the salmon coloring and then the blue coloring. All right, whenever you see the blue coloring, that indicates westerly winds. Now, if we look on the y-axis here, we're going from 100 millibar or hectopascal level all the way up high above the ground where we live, up into the area that is known as the stratosphere, the layer of the atmosphere that's known as the stratosphere. And you'll notice on the x-axis here we have varying years. So example here on the bottom left here is 1992, then we moved to 1997, 2002, all the way over to 2017. Now these are 5-year increments on the x-axis, the horizontal axis down here. So you notice if you just were looking at the color scheme here of this chart, this is the QBO, and it varies from a westerly regime where you see the blue coloring, and then the easterly wind regime in the stratosphere above the equator. That's that maroon shading. So blue westerly, maroonish color easterly, and so on. And it's fairly regular. You notice how it's fairly regular, the occurrence of how these colors alternate, all the way back from 1987 to 1992 in this area on the left, and then 2017 to 2022. All right, so we're going to examine this quasi-biennial oscillation, the QBO, and the U.S. winters. On the overview of the video, I am going to examine this QBO. I will look at the definition of the QBO. We will take a look at the QBO along with those U.S. winter temperature anomalies. And then finally, we'll conclude tonight's presentation with the impacts of the QBO along with other teleconnections or climate drivers. All right, so let's define this quasi-biennial oscillation, this QBO, first in tonight's video. It's a regular 2 to 3 year variation of the winds that blow in the equatorial region. Now, when I say equatorial, I'm referring to 5 degrees north latitude to 5 degrees south latitude. And these winds vary every 2 to 3 years, varying from east to westerly and back again. And it occurs in the layer of the atmosphere that's known as the stratosphere, between 16 and 50 kilometers above the Earth's surface. Now, I did note here that there's an average period of alternating wind regimes on the order of 28 months, or about 2.5 years. Now, the quasi-biennial oscillation, the QBO, is visible as downward propagating easterly and westerly wind regimes. And let's go back to the title slide. This is exactly what we're showing you. Those alternating westerly in the blue coloring, easterly in the salmon or red coloring, the alternating descending of these westerly and easterly winds that occur above the equator in the stratosphere. Due to its regularity between easterly and westerly winds, the QBO can be predicted with confidence several months ahead of time. Now, due to that regularity, now there has been cases where the QBO has not behaved like this, let's say, okay, where it didn't alternate perfectly over this period of 28 months. But for the most part, it's been a fairly regular occurrence. So it's fairly easier to forecast for the different phases of the QBO for specific winter seasons, or let's just say we can predict it with higher confidence, several months ahead of time. The QBO affects the stratospheric wind flow, additionally from the pole to pole, North Pole to South Pole, by modulating the effects of these extratropical waves. Now, that was discovered in a research paper by Baldwin and et al. Back in 2001. QBO also results in the modified vertical wind shear profiles that occur across the tropical regions. When I say vertical wind shear profiles, what I'm referring to vertical wind shear is a change in wind direction or speed with height over the tropical areas. And the QBO is also known to affect the climate phenomena outside tropical stratosphere. It can affect teleconnections or those climate drivers, including the North Atlantic Oscillation, the NAO, as well as the Madden-Julian Oscillation, the MJO. And that was discovered by research conducted by Anstey et al. Back in 2022, fairly recent research. Some of the history or background on the QBO. Following the 1883 volcanic eruption of Krakatoa, easterly winds were observed generally above the tropics at an altitude of 15 to 20 miles above the ground. A quarter of a century later, weather balloons were released over Central Africa, over the equatorial area, the central part of Africa, and those balloon soundings actually revealed a westerly wind in the lower stratosphere, counter to what was expected. So 1883, easterly winds were observed in the stratosphere, and then quarter of a century later down the line, weather balloons released collecting wind data reveal westerly winds, totally against what was initially discovered. So additional research was conducted, additional balloon launching, soundings, to where the QBO was really discovered in the 1950s, and it was discovered to feature a regular cycle of easterly and westerly winds in the tropical stratosphere. Here is another example. This source is NCEP NCAR. What I want you really to pay attention to, so we're going back to 1960 for the time period, the year, all the way out to the present time, 2023. And what I want to really have you focus on is the regularity of the cycles of these positive values above zero and the negative values below zero. This is the wind speeds, the zonal mean wind speeds in meters per second. And you'll notice a regularity between positive and negative phases. Whenever the QBO is on the positive side for wind speed, that generally indicates a westerly phase QBO. And whenever the wind speed is in the negative territory, like you see these dips here below the zero line, that is indicative of an easterly phase of the QBO. So a lot of regular cycle here from 1960 to present, showing a lot of ups, downs, ups, downs, ups, downs, all the way down the line. Let's now examine the QBO and U.S. winter temperatures. Now, this is courtesy of the World Climate Service. The following four slides are courtesy of the World Climate Service. And they have this particular graphic, which I really liked, to explain things. Generally on this graphic, is showing the probability of above and below normal temperatures for the United States during the winter season from December to February. The salmon coloring indicating above normal, probability of above normal temps. The blue shading or blue coloring indicating the probability of below normal temperatures. So during this easterly or negative phase of the QBO, much of the eastern U.S. is likely to see cooler than normal temperatures during the winter season between the months of December and February. Meanwhile, places west of the Rocky Mountains during the easterly phase or negative phase of the QBO, if you're west of the Rocky Mountains here along the U.S. West Coast, you typically see warmer than normal temperatures or a higher probability of those occurring, specifically here across the Pacific Northwest with this darker salmon color here. What about the QBO and U.S. winter precipitation? So during the easterly negative phase, if we keep on the easterly phase of the QBO, the Rocky Mountains, the western U.S. in general, the Ohio Valley, and the northeastern U.S., all the way down to the mid-Atlantic to Virginia, are likely to be drier, have a higher probability of being drier than normal. While the southern plains, right in this area, and the deep south are usually wetter than normal in the easterly phase of the QBO in the winter season. What about the westerly phases of the QBO? What is the westerly phase of the QBO? What's its impact on U.S. winter temperatures for the months of December, January, and February? Much of the northern U.S. during the westerly phase of the QBO is more likely to be cooler than normal. See the blue shading here? Higher probability of cooler than normal, whereas parts of the southwestern U.S. are warmer than normal. Higher probability of warmer than normal temps during a westerly phase of the QBO. Looking at the precipitation anomalies during the westerly positive phase of the QBO, the upper Midwest tends to have above normal precip, as well as the northern Rockies, as well as California. While the southern U.S., the south, as well as the eastern U.S. are more likely to be drier than normal during that westerly positive phase of the QBO. And then one other thing I want to mention is these are the different years that we saw in easterly negative phase of the QBO right here. They're listed here in the chart as recent as 2017. And then for the westerly positive phase of the QBO, these were the winter seasons or the years that featured the westerly positive phase. So 66 all the way, 1966 all the way up as recent as 2016. Now, let's continue moving on here. What I next went to was I looked at specific winter months. My winter season is December, January, February, those months. And I looked at higher magnitude of the QBO, higher numbers or values of the QBO, whether they be negative or positive. I looked at both. So we start off with December of 1989. These were the mean or average temperature anomalies for the month of December of 1989. And it was a frigid month across the eastern U.S. in December of 89. And you notice this purple shading, this magenta purple shading, temperatures were running as much as 15 degrees Fahrenheit below normal from New England down to the Ohio Valley. Mid-Atlantic, 12 degrees below normal. Even you in the Midwest across Missouri and Iowa, 11 to 13 degrees Fahrenheit below normal. While the western U.S. was enjoying a milder December in 1989. Now, what was the QBO value that particular month? It was negative 8.47. So fairly significantly negative. This would indicate we were in the easterly QBO phase, and this matches up well with what we just looked at, right? We said the easterly or negative phase of the QBO generally correlates to a higher probability of below normal temperatures in this area. Southern plains, Midwest to the eastern seaboard. And we got that in December of 89. December 1990, now we're going to flip the script and we're going to look at a positive QBO value of 8.93. Now remember, positive values, when we're talking QBO, that equates to westerly winds in the stratosphere above the equator, in the equatorial areas between 5 degrees north and 5 degrees south. So what did that do to the United States weather temperature anomalies? We had above normal temperatures across the eastern U.S. on the order of 3 to 5 degrees Fahrenheit in December of 1990. They were above normal. And then we had below normal temperatures out in the west. Now, does this correlate well with that westerly positive phase of the QBO? Let's see. Let's go back. Westerly positive phase of the QBO in winter temperatures here. This is where you'd expect milder temperatures, and this is where you'd expect some pockets of warmer than normal temperatures or near normal temperatures in the white. So what happened here? Not exactly what you'd expect. I mean, you did see a very well below normal temperature regime across Montana, Idaho, eastern Oregon, down to northern Nevada, right here in this area, Wyoming included. But it does match up with the eastern, what we'd expect. With positive QBO, we would expect milder than normal temps. What about December of 2003? What were the mean temperature anomalies look like that particular month? Below normal along the mid-Atlantic specifically, and it got more significantly below normal, this green shading across Florida, Georgia, and South Carolina here, on the order of 4 to 6 degrees Fahrenheit below normal. Meanwhile, the northern plains were the mildest, 4 to 6 degrees Fahrenheit above normal temperatures in December 2003. And the QBO that particular month was minus 9.14, so fairly significantly negative for the QBO. We're in the easterly phase of the QBO in December of 2003. All right, and so this kind of matches up with what we'd expect, below normal temperatures in the east. We look at December 2013 mean temperature anomalies. Now we have milder than normal temperatures, just slightly above normal, 1 to 2 degrees Fahrenheit above normal across Virginia down to North Carolina. And then the temperature anomalies got a little bit more above normal down towards southern Georgia and Florida at 4 degrees Fahrenheit above normal. And look at how much below normal the temperatures were in the upper Midwest and the northern plain states. The icebox of America, International Falls, was 15 degrees Fahrenheit below normal for December of 2013. So, yeah, I mean, we saw below normal temperatures in the green shading right down to Kansas, Oklahoma, and North Texas. And the QBO this particular month in December 2013 was fairly significantly positive at plus 9.92. How does that match up? QBO and U.S. winter temperatures, when we're talking about the westerly positive phase, much of the northern U.S. is more likely to be colder than normal. Now, was it for that particular time? Let's go look back. It was. So that matched up fairly well. Look how much below normal the northern U.S. was with a positive phase of the QBO. What about the January? Now, this was this recent past winter, 22-23. January 2023 mean temperature anomalies well above normal. Midwest up to New England. We're talking 9 to 11 degrees Fahrenheit above normal in this area. 7 degrees Fahrenheit across Virginia and the Carolinas. And then well above normal in Texas, Louisiana, Arkansas, Mississippi. See that? And what we saw in January of this year, 2023, we saw a QBO value of plus 7.92. So last winter, we were in the positive phase of the QBO. All right, so I kind of zoned in on a couple specific winter months, and that was my goal. Examining the QBO values, which I picked up directly from NOAA, and just compared what the anomalies look like, what the temperature anomalies look like, and did they match up with what we'd expect here, what we've already covered right here. Easterly or negative phase of the QBO temp anomalies, precip anomalies. We didn't get the precip, but we did look at specifically honing in on the temperature, winter temperature anomalies based on the negative and positive phases of the QBO. Now let's move forward. Why is the QBO so very important? You know, you're thinking to yourself, we're examining stratospheric winds, whether they're blowing from the west or the east, well up into the stratosphere above the equatorial area. Why does this matter? This chart, which was produced by Gray et al. In 2018, their research paper, this shows you why it's so important, okay? There's 3 different routes. They call them routes in their research. The blue arrow indicates the polar route. The purple coloring here, these arrows indicate the subtropical route, and the red colored arrows indicate the tropical route. Okay? Now, we're focused solely on the winter months here. That's why we're on this side of the diagram, on the right side. Okay? Holton and Tan back in 1980 as well as 1982 discovered some interesting things, as well as Baldwin and Dunkerton in 2001. They discovered this polar route when you have this QBO in a negative easterly phase. This polar route of the QBO, where it's seeing energy transferred, it modulates the strength of the stratospheric polar vortex via wave breaking action from the troposphere to the stratosphere. Okay, so just by the fact that these winds are easterly up in the stratosphere over the equatorial areas, you see the latitudes here on the x-axis. You see Holton and Tan discover this polar route modulates the strength of the stratospheric polar vortex, which then influences the tropospheric circulation and also affects the surface temperature and pressure distribution. So follow the blue route here. QBO, easterly winds in the stratosphere over the equatorial areas, right? And then it impacts the strength of the stratospheric polar vortex, which then impacts the surface temperature and pressure distribution, specifically in the form of the NAO, North Atlantic Oscillation. We'll get more into that here in a moment. That's just the polar route of why the QBO is important. Bottom line is you get this reflection or refraction, these planetary waves towards higher latitudes, which occur during this easterly QBO phase. Reflection or refraction of planetary waves, wave breaking. By the way, on this chart too, I wanted to mention that the solid contours, these solid dark black lines, indicate westerly winds, whereas the dashed contour lines over here indicate easterly winds. And then the gray scale, you see the different shades of gray here on this? That indicates standard deviation of the zonal winds in meters per second, with the darker gray shading indicating greater deviation. Okay. All right. So that's the polar route. It can have a major impact, QBO, on the strength of the stratospheric polar vortex, which ties into what type of upper level pattern sets up for the winter season. Additionally, we have this subtropical route, which involves, I won't get too much deep into it, but it's a thermal wind balance, the QBO, the convection associated over the tropical areas. It can induce meridional circulations. It can also, the QBO can really tie in with the strength of the subtropical jet stream, as well as some of the steep convection, as I mentioned, can result in increased areas of precipitation. And then finally, we look at this right here, the red, these red arrows. QBO goes directly to deep convection. Specific areas of the tropics are more favorable to see the deeper convection in showers, and heavier precipitation occurs in specific areas of the equatorial areas. Okay. Additionally, there's your planetary waves here via the tropical route. Okay, so this really explains a lot. Okay, so there's a lot of moving pieces is what I'm getting at with this. It looks like a complicated diagram, doesn't it? But it really isn't. There's different routes or mechanisms at which QBO plays into the mid-latitude and high-latitude weather patterns, specifically pressure and temperature distribution. All right, so now we're going to look a little bit closer at the QBO and its relationship to other teleconnections or climate drivers. We'll start with the stratospheric polar vortex. I took all of this from the research that's out there. First bullet, QBO influences the strength of the stratospheric polar vortex, which influences those surface pressure patterns. And Holton and Tan, 1980, came up with that, as well as Baldwin and Dunkerton in 2001. They both talked about this. The easterly QBO phase is generally associated with a weaker stratospheric polar vortex. Now that's interesting. That was research conducted by Anstey and Shepard back in 2014. By the way, you get easterly QBO, you get a weaker stratospheric polar vortex. What happens next in the domino effect? You get more sudden stratospheric warmings. You get a weaker Atlantic jet stream, and you get colder winters in the eastern U.S. So it's all connected. What happens in that wind field above the equator in the stratosphere really does matter to mid-latitude weather in the winter, believe it or not. Whereas you get a westerly QBO phase, that's going to be associated with opposite effects of the easterly phase. So westerly QBO phase, think colder, stronger, more symmetrical or circular shaped stratospheric polar vortex. That's the same research paper, Anstey and Shepard in 2014. And whenever you get the stronger, colder temperatures in the stratosphere, stronger polar vortex, more symmetrically shaped, it coincides with milder winters in the eastern U.S. and a stronger Atlantic jet stream. Now, the stratospheric polar vortex variability may also be influenced by the solar cycle, which is the 11-year cycle, the El Nino Southern Oscillation, whether we're El Nino or La Nina for the winter, and other sources of tropospheric variability. So there's other climate drivers of teleconnections out there that can really play into the strength and the variability in particular of the stratospheric polar vortex. This is an excellent diagram that I picked up. Now this one is from Liu et al. 2014 research paper, and then Yu and Sun in 2016. Okay, I'm showing you on the left QBO in easterly phase. On the right, this is QBO in the westerly phase. Look at the differences here. So in the easterly phase in the stratosphere, we have easterly winds in the stratosphere above the equatorial area. We have a colder, higher tropopause, which is that transition point between the layer of weather near the surface, the troposphere, and that layer above the troposphere, the stratosphere. So colder and higher tropopause. Over here on the right with the QBO westerly phase, you get westerly winds in the stratosphere over the equatorial areas, and you get a warmer and lower tropopause, so opposite effects. And then look what happens here. I really want you to focus in on the strength of the MJO. With the QBO easterly phase, you're going to get sinking air. You get increased MJO effects with the easterly phase, more increased MJO strength and activity. You get sinking vertical motion over Indonesia there. indicated by this downward brown arrow. And then you get more increased upward vertical motion over the central equatorial Pacific. So you get more precipitation at the surface over the central equatorial Pacific around the dateline. And you get sinking air and drought conditions across Indonesia, even extends during El Nino all the way over to Australia. With the easterly phase of the QBO, additionally, you get a slower eastward MJO propagation, more increased MJO predictability. Whereas the westerly phase of the QBO here, the diagram on the right, we still get the sinking air motion in the Indonesia area. However, it's decreased MJO strength, so not as strong during a QBO westerly phase for the MJO. Activity not as great. You get faster moving eastward MJO propagation during the QBO westerly phase, and then you still get that upward vertical motion generally over the Western Pacific in this case. Right from the research by Liu et al. As well as Yu and Sun, you get stronger, more organized MJO convection across the Western Pacific. So when I have more convection and thunderstorms and rain across the Western Pacific, that means my MJO is stronger in phases 6 and 7 during easterly QBO winters. So very interesting research. When we look at QBO and the NAO, the North Atlantic Oscillation, I mean, can you believe that the QBO and the rainfall in the tropics can actually influence the North Atlantic Oscillation in different ways? I mean, we're talking all the way across the North Atlantic from the equatorial Pacific. Easterly QBO tends to generate more negative NAO phases. Now that's interesting, right? The easterly phase of the QBO, more negative NAO phases blocking over the North Atlantic and Scandinavia. And that's generally associated with increasing frequency of sudden stratospheric warming events. Easterly QBO phase, more negative NAO phases, high latitude blocking over North Atlantic and Scandinavia, increasing frequency of sudden stratospheric warming events. I had to repeat it, it's important. Look at the graphic here in the bottom right. This was produced by research conducted by Salminen et al. In 2020. This is showing you the frequency of sudden stratospheric warming events. All right, and the number of winters is over here on the y-axis. When we have a QBO in the easterly phase, QBOE, we had over the whole realm of winters that we looked at, or that they looked at, Salminen et al., 21 winters saw, during the QBO easterly phase, saw a sudden stratospheric warming, as compared to only 10 when the QBO was in the westerly phase. So ratio basically of 2 to 1. Twice as many sudden stratospheric warming events occurred during a QBO easterly phase as compared to the QBO westerly phase. By the way, these blue bars in the values indicate non-sudden stratospheric warming winters. Okay? So that's a big difference. 21 versus 10. QBO easterly phase 21, QBO westerly phase 10 sudden stratospheric warming events. If we look at the negative QBO, the easterly phase of the QBO, along with a negative NAO, look at what you get. These are the temperature anomalies on the left, the purple and the blue indicating well below normal temperature anomalies for the months of December, January, and February. And you were talking well below normal, Midwest to really focus on the Midwest, but it does bleed over a little bit towards New England and the Mid-Atlantic. If we look at the graphic here on the right, these are your 500 millibar height anomalies, purple and blue indicating below normal height anomalies associated with colder temperatures and troughing. And then the yellow and orange colorings, look at the orange coloring here on the right-hand graphic of 500 millibar height anomalies, well above normal, the orange coloring, indicates anomalously high heights over the North Atlantic, over Greenland, as well as over Scandinavia to the high latitudes. Look at the ring of purples all the way around the globe in the mid-latitudes, starting from the Midwestern U.S. all the way across the North Atlantic into Europe, parts of Asia and Siberia. So this is what happens, colder and stormier winters for the Midwest as well as the Eastern U.S. when you get a easterly phase QBO along with a negative NAO. You get high latitude ridging or blocking in this location. Now, what happens if we combine QBO and the El Nino Southern Oscillation, the ENSO? During westerly QBOs, the polar vortex and subtropical jet stream are enhanced. When I say enhanced, I mean stronger. So The polar vortex is actually stronger during westerly QBOs, and the subtropical jet stream is also stronger. QBO signals in the polar vortex are amplified during La Nina. Well, that's interesting. So we're saying during La Nina winter seasons, the QBO signals for the polar vortex are more amplified, courtesy of Kumar et al. 2022. And then during El Nino westerly QBOs, when you get those two combinations, El Nino and westerly QBOs, the strongest subtropical jets occur. Well, we have El Nino coming up this winter season, and I'm going to tell you right now, we're expecting an easterly phase of the QBO this upcoming winter. So we won't quite have this combination, at least in the forecast for the upcoming winter, 23-24 winter. Now with an easterly QBO and El Nino, so this is what we will see this winter. The combination of easterly QBO and El Nino. You generally get an upper ridge over the North Atlantic, and Kumar et al. Just released a research paper last year in 2022 on this relationship. And the QBO signal is enhanced during La Nina and is nearly absent during El Nino. So take this with a grain of salt, but what Kumar et al. Discovered is the QBO signal is generally enhanced during La Nina and not so much during El Nino. So in summary, tonight's presentation, here is my closing thoughts. The QBO impacts atmospheric circulation across not only the tropical areas, but also the mid-latitudes as well as the high-latitude areas. We looked at this. This kind of told us that. 0 degrees latitude all the way up to 60 degrees in the high latitudes, the Arctic area, with that stratospheric polar vortex, okay? So we know there is a relationship between QBO at low latitudes all the way to the mid-latitudes with subtropical jet, all the way up to the high latitudes with that stratospheric polar vortex, okay? Not all temperature anomaly outcomes, when I looked at this, were in accordance with easterly QBO phases. In other words, not all temperature anomalies were colder than normal in the eastern U.S. I didn't show you any of those graphics, but like all these monthly outputs, I'm showing you these mean temperature anomalies. We looked at what actually lines up fairly well with the phase of the QBO, whether it be positive or westerly versus negative or easterly. There were some cases where I looked at some monthly temperature anomalies during the winter season, December, January, and February, with these QBO values here. And for example, the positive values should correlate with milder temperatures in the east. They did not. So there were some cases that I did not present that definitely have some opposite effects of what you'd expect with, in particular, I was looking at the easterly QBO phase. Now the strength as well as the phase, strength is also an important consideration when we're talking QBO. Generally, the weaker the QBO, the less likely the sensible weather will align properly, as we'd expect. And other teleconnections or climate drivers can actually be more influential in a particular winter season in determining those winter temperature anomalies, as well as those precip anomalies, really. So you might have an easterly phase QBO, and you're like, okay, well, we should be colder than normal in the eastern U.S. this winter. But then all of a sudden you get a negative PNA, Pacific North American pattern, with the trough out in the western U.S., and that is going to indicate above normal temperatures in the east. So then you have to look at the magnitude of the teleconnections to determine which one is going to be more dominant. Additionally, we are expecting an easterly QBO phase this upcoming winter, the 23-24 winter season. And with that in mind, we would expect to see more upper level ridging over the North Atlantic and a negative phase NAO with prolonged blocking pattern. This is going to result in increased probability for a sudden stratospheric warming event and a weaker stratospheric polar vortex overall for the winter season. Research conducted by Kai et al. In 2022, just last year, they determined that November, December, they consider this the early winter season, early portion of the winter season, November and December. Those NAO signal, that persists into January during easterly QBO phases. And additionally, when you have easterly phase QBO, you get stronger stratosphere-troposphere connection in early winter. Now the combination of El Nino plus an easterly QBO favor increased probability for winter weather across the southeastern U.S. Both of these favor it. El Nino favors a more southern storm track, as well as below normal temperatures for the southeastern U.S., and the easterly phase of the QBO does the same, more below normal temps for the southeast. All right, that wraps up my video this evening. I hope you enjoyed it. Just kind of covering the Quasi-Biennial Oscillation. I will be looking at some other interesting features and videos ahead. Specifically, I want to take a look at the Pacific Decadal Oscillation as well, and just determine the difference between positive versus negative phases of the PDO. What those water temperature anomalies are off the west coast of the United States, specifically over the eastern North Pacific, and what that could potentially mean for downstream weather during the winter season across the U.S. All right, I thank you so much for subscribing to the Spot on Weather YouTube channel, and until next time, everybody, take care and God bless.